Hello, in this video we shall begin with a new chapter of discussion, that is magnetism and matter. Now the word magnetism, or the word magnet, is derived from the ancient island in Greece called Magnesia, where the first traces of magnetism were found. Now, in the year 600 BC, it so happened that the shepherds, they started complaining about their shoes getting attracted by uh, getting attracted because their shoes had iron nails, and so was the case with the sticks that they used to hold, which were iron tipped, the rods. So this was the first instance where one associated with magnetism, or one associated magnetism at a particular place where it was uh, where the magnetic iron ores were obtained. Basically, as you might have known already, that magnetism is associated with hard iron. It's typically magnetite, or lodestone is a good example. Lodestone, or even lodestone, LOAD, is also correct. It is nothing but magnetite, iron magnetite. This was obtained in great amount from that place, and basically the properties of magnets, as we observe in our day-to-day life, is that when we suspend a magnet, a long magnetic bar, then it aligns itself in the geographic north-south direction, and the part of the bar magnet which faces the, or which is directed towards nearly the north pole of the earth, is the north pole of the magnet, and the other end is obviously the south pole of the magnet, which gives us a brief idea about the earth's magnetism, because we already know from previous from our junior classes that we've already studied that the like poles, they repel each other, while the unlike poles attract each other. So in case of the earth, this is the earth has its own magnetism. Okay, the molten material that is present inside the earth in its core is the reason for its magnetism. The iron and nickel, the molten state of the iron and nickel and various metals, they give its property of magnetism to it. And suppose it is the tilted axis of the earth. This is the geographic axis that we know is tilted, and it's the geographic north pole, and this is the geographic south pole. And then we have the earth's magnetic meridian, which actually is slightly off the uh, poles, the geographic poles, because they are at an angle of nearly varying between 10 to 15 degrees, or somewhere it's even 17 degrees in some of the books that you can consider. So this is more or less a tilted, further tilt in the magnetic meridian, or the magnetic line along which the magnetism is observed. And This, suppose, is a small magnet. It's not small, it's not to the scale, but still a small bar magnet. If I hold it, if I suspend it freely, then its north pole is directed along this direction and its south pole is directed along this direction. Means the south pole is almost towards the geographic south, while its north pole is almost near the geographic north. But as we know that opposite poles attract each other, so we can say that the Earth's magnetic south is the one that attracts the north pole of the suspended bar magnet, and the magnetic north is what attracts the south pole of the suspended bar magnet. So this is the alignment of the magnetic meridian of the Earth. This is the Earth's magnetic meridian. And as I said, it is slightly tilted in some of the values may vary. Some of the books you can at present, the value that you can find is varying between 11 degrees to almost 17 degrees, but that's for the texts. We haven't practically uh, we can practically obtain that by suspending magnet ourselves, uh, but that's a separate practical class that you can have and experience the variation in those numbers. Now, we will be discussing in details about the Earth's magnetic field and many more things that are associated with the Earth, but first and foremost, the magnetism overall. Now, let's take the example of the good old bar magnet that we have been discussing about. Now, this is what a bar magnet usually looks like. It's in the form of a bar, and if we place it aligned to this magnetic meridian just like this that we have done, we start tracing the lines of force or the impact or the line along which the magnet tends to apply force on iron fillings, then we will find that just by dropping the iron fillings, some of the iron fillings around it, the iron fillings tend to re you know relocate themselves along certain lines, suggesting that there is definitely the presence of certain lines of force along which this magnetism works. So let us suppose this is the north pole. I'm considering this case only, and here I have the north pole aligned to the magnetic south of the earth, and here I have the south pole aligned to the magnetic north of the earth. That means this north pole is pointing to the geographic north and the south pole is pointing almost to the geographic south. And in that case, what we find is the iron fillings or even the magnetic needle that will tend to trace this kind of a track or this along this dashed line that I'm showing you right now, almost like this. Experimentally, you will have a better idea about this entire thing. So this is one of those, or these are a couple of those lines. This also gives us the case where the lines of force are always directed out of the North Pole and towards the South Pole externally, and internally they move from south towards the north, which can again be traced by those uh, needle or those iron fillings. Uh, and these are the two lines. You can have more of these lines. Remember, you will have a huge concentration of lines of force towards the North Pole and towards the South Pole, because there the intensity of the magnetic force is obviously pretty high. And here, as you move away from the magnet at these points that I've just ticked, the intensity gradually decreases, and you have these points closer to the magnet, just besides them, where the magnetic lines of force obviously make do not have any such impact immediately to the side of the bar magnet. And gradually what you can also find is that these lines of force will interact with the Earth's magnetic lines of force, and finally they will cancel out each other to give you a null point somewhere over here. This is the null point. As we proceed further tracing those lines of force, these lines will gradually move away like this, right? And they will be entering into the South Pole like this. Design is very beautiful, the interaction of nature, but that's for the practical lessons in case you uh, wish to. But these are the null points you will gradually experience, and finally you will also have these lines of force going like this, but this will be in the opposite sense like this. This is the Earth's, mostly it's the Earth's field which tends to interact with the field of this magnet, and then cancelling out each other, you finally have the null point on this side, which will be the same on the other side, but I've written stuff over there, so I won't be tracing or won't be giving you on that side on the top. So this is how the field lines interact. Obviously, from electrostatics, we have understood that the field lines definitely give rise, or they tell us about the lines of force. That means these are the lines along which the magnetic force is acting. And so is the case with a magnetic field. The field lines obviously denote the direction of the magnetic field. Now, with such ideas available to us, we can draw comparisons with electrostatics, the magnetostatics part of it. We can have a similarity with electrostatics. Now, the Coulomb's law in electrostatics had provided us with the force between two charges. Here we have the poles, the North Pole and the South Pole. Now, these are dipoles. They can never exist as a monopole, because however small you may cut the magnet, if one of the faces, if I start cutting it and I cut down very thin piece right in front over there, then what I'll find is that if one of the faces is the North Pole over here, then the other face has to be the South Pole. So the magnet always exists in the form of a dipole and never as a monopole, whereas in case of electric charge, you had isolated positive as well as negative charges. Now, these dipoles have the same pole strength, that we call it. Pole strength is analogous to the electric charge, that is the value of electric charge in case of electrostatics. In magnetostatics, however, you have these poles which have a certain strength, or even they are, in some of the books you can find, they are termed as a magnetic charge. Now, if we consider a bar magnet again, then we find that these poles are somewhat located a bit inside the magnet, just like the dots that I have represented over there. So the north and the south pole forming the magnetic dipole are located inside, a bit inside the magnet from one end from both the ends actually. And the distance here is actually the magnetic length. The distance here is the magnetic length, which is the length between the two poles of the magnet. So the magnetic length is obviously smaller than the geometric length. This is the geometric length. Let me draw it a bigger one for you. So the magnetic length is obviously smaller than the geometric length of the given magnet. Approximately the magnetic length, let me write it as ml and gl. So the magnetic length is somewhat nearly 80%, 6 by 7, or even 85% nearly. So on an average it is 83 to 85%. The length of the geometric, or the 85% of the geometric length. So this is how the two lengths are compared. Now each pole, as I mentioned, has a pole strength, and in case of dipoles, magnetic dipoles, the pole strengths are obviously the same. Usually the pole strengths are represented by small m, or even magnetic charge, magnetic charge or pole strength of a magnet, usually represented by small m or even q subscript m. We'll be using this notation for your for this explanation. Now what does the Coulomb's law in magnetostatic tell us? Well, it states that Coulomb's law in magnetostatics that states that if we have two magnetic poles, one of the poles, this is one part of one magnet, and this maybe is another part of another magnet, and this has a supposedly a pole strength of qm1, and this has a pole strength of qm2, then we, and they're separated by a distance r, then we can say that the force is exactly as in the case of uh, force between electric charges. The force between two magnetic charges or magnetic poles that are present over there separated by a distance r is directly proportional to the product of those pole strengths and inversely proportional to the square of the distance separating them. So this can be rewritten as the proportionality of the product of the pole strengths divided by the square of the distance. And for obtaining an equation, we multiply it with a constant. That constant is k. I've written it k over here. What is that value of k? K has a certain value and an expression as well as in case of the electrostatic forces. K here is mu naught divided by 4 pi. Mu naught, just like epsilon naught was in case of, in the electrostatic case, mu naught is known as permeability. That was permittivity, and this is permeability, telling us how permeable is the magnet to allow the lines of force to interact, or how permeable is a medium to allow those magnetic lines of force to pass through it. So the permeability of the given space here is, it is vacuum, air or vacuum, and that has a value of 4 pi times of 10 to the power minus 7. That 4 pi divided by the 4 pi, that means the value of k is simply 10 to the power minus 7. The units will be dealt shortly. Because the magnetic charge or the pole strengths that we consider over here Those pole strengths have a unit of ampere times of meter. We'll be knowing why later on, but as of now you can just know that it is ampere times of meter. And then you have the value of you have the unit for distance as meter, so ampere squared meter squared over here, in case of the right hand side, divided by meter squared, so the meter squareds can get cancelled out. We are obtaining the value, we are obtaining the unit of k. So k has the unit of simply Newton per ampere to the power minus 2. This is the unit of k. And as for permeability, it has the same unit because it is in the numerator, as opposed to permittivity in case of electrostatics, which had exactly the inverse of unit of k. Similarly, from that we can obtain the dimension. Now, the dimension in case of the pole strengths is simply ampere times of meter, that means L and A. And in case of the proportionality constant or even mu naught, that is the permeability of free space, we have it to be equal to m L t to the power minus 2, that is in case of force, and A to the power minus 2, that is for ampere to the power minus 2. So this is the dimension of the value of the permeability as well as the constant k. Now these are some of the things that we discuss up first in this topic. We'll be discussing more. This will probably be a series of 3 to 4 videos. Stay tuned for it. Till the next time, thank you.